So far, you have been representing graphs as collections of points x and y on the rectangular coordinate system. The corresponding equations for these graphs have been in either rectangular or parametric form. In this video, you will study a coordinate system called the polar coordinate system, which is more convenient for many purposes. Please don't forget to click the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. One way to specify the location of point P is to use a rectangular or Cartesian coordinate system. This system has two perpendicular axes, x and y, that meet at the origin. Each axis is like a number ruler. The location of P is given by a pair of coordinates x and y. X is the horizontal displacement from the origin, and y is the vertical displacement from the point reached on the x-axis. The coordinate pair x and y describes the position of point P relative to the origin. The system is called rectangular or orthogonal because the axes intersect at a 90-degree angle at the origin. Furthermore, the lines leading to the coordinates of P form a rectangle with sides of length x and y. Notice that we talk about the displacement and not the distance. This is because in this system we need to use the directions indicated by the arrows to help us to be able to specify a point uniquely. Thus, moving up from the origin is a positive displacement, whereas moving down from the origin is a negative displacement. Similarly, moving to the right from the origin gives a positive displacement, and moving to the left gives a negative displacement. The name honors the French mathematician René Descartes, who used this system extensively. To determine the location of a point P, an alternative to the Cartesian system is the polar coordinate system. In this system, we measure the distance r from point P to the origin, called the pole. However, since multiple points cannot be at the same distance r from the pole, forming a circle, we need an additional piece of information. This information is the angle theta, measured from a reference line, the polar axis, which also passes through the pole. The line connecting the pole to point P forms this angle theta with the polar axis. The polar coordinate system is also considered orthogonal because at any given point, the tangent to a circle is perpendicular to a radial line passing through that point. In other words, when r and theta intersect, they do so at a right angle, 90 degrees. This perpendicularity is the defining characteristic of an orthogonal system. The other pair, r and theta, uniquely describes the position of point P. The system lends itself particularly well to spiraling curves that spiral about a point and closed curves that have a high degree of symmetry. Polar coordinates have been developed by various mathematicians throughout history. Key figures include Isaac Newton, Jacob Bernoulli, and Grégoire de Saint-Vincent, who contributed to the formalization and application of polar coordinates between the 17th and 19th centuries. A polar coordinate system is a two-dimensional coordinate system that defines the position of a point in a plane using two primary values. Radial coordinate r. This represents the distance of the point from a fixed reference point called the pole. The pole is analogous to the origin in a Cartesian coordinate system. Angular coordinate theta represents the angle measured from a fixed reference ray called the polar axis to the line segment connecting the pole to the point. The polar axis is typically a ray extending horizontally to the right from the pole, similar to the positive x-axis in a Cartesian system. Angles are generally measured counterclockwise from the polar axis and can be expressed in degrees or radians. The position of any point in the plane is then determined by its polar coordinates, r and theta. Let's see how the polar coordinate system works. To plot the points with polar coordinates, follow these steps. Begin by drawing a central point, known as the pole. This is analogous to the origin in a Cartesian coordinate system. From the pole, draw a horizontal line extending to the right. This line is the polar axis, similar to the positive x-axis. Starting from the polar axis, which represents an angle of 0 radians, rotate counterclockwise by the specified angle pi over 6 radians. Draw a line segment extending from the pole along this angle. Along the line segment you just drew, measure a distance of 3 units from the pole. The location at the end of your measured distance 3 is the point in polar coordinates. To solve part B, begin by drawing the pole. Then draw the polar axis extending to the right from the pole. As in trigonometry, the angle theta is measured counterclockwise for positive values and clockwise for negative values. Since we are rotating by an angle of minus pi over 3 radians, that is, clockwise, draw a line segment from the pole in that direction. Along this line segment, measure a distance of 2 units from the pole to locate the point. A few notes are necessary before proceeding. The origin does not have a well-defined angular coordinate, so we assign to it the polar coordinates 0 and theta for any angle theta. In the rectangular coordinate system, each point has unique coordinates, but this does not apply to polar coordinates. The key difference is that an angle point can have multiple sets of polar coordinates. This is because angles that differ by a multiple of 2 pi have the same terminal point, whether you go around the circle clockwise or counterclockwise. Adding or subtracting full rotations brings you back to the same angular position. The angular coordinate is not unique because if a point P has polar coordinates r and theta, then adding or subtracting full rotations label the same point for any integer n. As defined above, the radial coordinate r of a point P is non-negative, since it represents the distance from P to the pole. But there are occasions when we wish to allow r to be negative. Look at the examples. Plot the point P with radial coordinate of 5 units and angular coordinate of 4 pi over 3 radians. The point P can be reached by turning 4 pi over 3 radians counterclockwise from the polar axis and drawing a line segment from the pole in that direction. After that, along this line segment, measure a distance of 5 units from the pole to locate the point P. Plot the point Q with radial coordinate of minus 5 units and angular coordinate of pi over 3 radians. The point Q can be reached by turning p over 3 radians counterclockwise from the polar axis and drawing a line segment from the pole in that direction. After that, along this line segment, measure backward 5 units from the pole to locate the point Q. You can observe that the points P and Q describe the same point. The correct interpretation for this negative distance is that it represents a positive distance measured in the opposite direction, just as the minus sign in front of a vector indicates that the direction of the vector is opposite to the reference direction, while the length remains the same. By convention, we allow negative radial coordinates. Adding pi to the angular coordinate is equivalent to changing the sign of the radial coordinate. With this convention, these two polar coordinates represent the same point. The polar coordinates of a point are not unique. The two main reasons are the periodicity of the angles and the negative radial coordinate. To make polar coordinates unique for any point except the origin, we impose a few restrictions. We can specify unique polar coordinates for points other than the origin by taking radial coordinate positive and the angle theta between 0 and 2 pi radians. We define the radial coordinate to always be positive. This ensures the radial coordinate represents a true distance and avoids confusion with the idea of walking backward. We limit the value of the angle theta to be between 0 and 2 pi radians, ensuring that the angle theta rotates counterclockwise for a single full turn. Let's see how it works. Let's solve part A. Since the radial coordinates are negative, we must add pi radians to the angular coordinates. After that, simply locate the points as we did before. To solve part B, we must add 2 pi times n to obtain all the polar coordinates of these points. While rectangular coordinates are excellent for representing some linear relationships and motion, polar coordinates are excellent for describing others. In calculus, choosing the appropriate coordinate system can greatly simplify integration, so you should master the conversion between these two systems, and you can do so using basic trigonometry. Polar coordinates are expressed as r and theta, while rectangular coordinates are expressed as x and y. Converting polar coordinates to rectangular coordinates means expressing the polar coordinates as rectangular coordinates. Since the polar axis coincides with the x-axis and the pole coincides with the origin, a relationship can be established between polar coordinates and rectangular coordinates for a point. The radial coordinate is obtained by the Pythagorean theorem. The x-coordinate is obtained by noting that x is the side adjacent to theta in a right triangle. and the y-coordinate is the side opposite theta. The relation between polar coordinates and rectangular coordinates is given by the following equations. Let's see how it works. Convert each of the following points into the given coordinate system. To solve part A, we convert from polar to Cartesian coordinates. The angle 2 pi over 3 radians is located in the second quadrant. In this quadrant, the cosine function is negative and the sine function is positive. Specifically, the value of cosine of 2 pi over 3 is minus a half, and the value of sine of 2 pi over 3 is the square root of 3 over 2. To solve part B, we convert from Cartesian to polar coordinates. First, we find the radial coordinate. After that, we find the angular coordinate. We must find the angle theta whose tangent is minus the square root of 3 divided by 3. And tangent negative occurs in the second and fourth quadrants. To determine the quadrant, we look at the signs of the x-coordinate and the y-coordinate. The x-coordinate is negative and the y-coordinate is positive. A point with a negative x-coordinate and a positive y-coordinate lies in the second quadrant. We know that tangent of pi over 6 equals square root of 3 divided by 3. And this means our reference angle is pi over 6 radians. In the second quadrant, the angle is 5 pi over 6 radians. The polar coordinates with the positive radial coordinate are given as follows. If we wish to use the negative radial coordinate, then the angle becomes 11 pi over 6 radians. Note that you can also use the equations above to convert a polar equation to a rectangular equation and vice versa. Let's see how this works. To solve part A, replace x with r times cosine of theta and divide both sides by cosine of theta, where the secant of theta is the inverse of the cosine of theta. To solve part B, subtract 2x from both sides. Replace x with r times cosine of theta and y with r times sine of theta. Let's rearrange the terms and factor out r from the left side, and finally solve for x. To solve part C, replace x with r times cosine of theta and y with r times sine of theta. Then, dividing by r times cosine squared of theta, we get tangent is the ratio of sine to cosine, and the secant of theta is the inverse of the cosine of theta. Now we'll convert polar equations to rectangular equations. To solve part A, we replace r with the quadratic expression above. Squaring both sides, we obtain the equation of a circle with a radius of 6 units centered at the origin. To solve part B, We begin by multiplying both sides by r and making the appropriate substitutions to arrive at the expression. By moving 2y and adding 1 to both sides, we obtain the equation of a circle with a radius of 1 centered at the coordinates x equals 0 and y equals 1. To solve part C, we begin by multiplying both sides of the equation by 3 minus cosine of theta, and making the appropriate substitutions to arrive at the expression. By moving x, squaring, and simplifying, we obtain the expression. After further algebraic manipulation, we arrive at the equation of the ellipse.